The next problem is called target sum. We are given an integer array nums and an integer called target. We want to build an expression out of the nums, so elements in the input array, by adding one of the symbols, so plus or minus, before each integer in nums, and then concatenate all the integers. For example, if we have nums 2 and 1, so we can only choose from 2 and 1, we can add plus before 2 and the minus before 1, and then basically concatenate them to the expression plus 2 minus 1 to get the total sum of 1. We have to return the number of different expressions that we can build which evaluate target. So in this case, we are assuming the target would be equal to 1. The first example is basically all the 5. We only have 5 ones, and the target is 3. And these are the 5 ways that we can add the pluses or minuses to the each of the elements inside of the input array to get the target 3. So let's just do the first example. So we are adding the 4 ones. So we'll have minus 1 plus 4, which is equal to 3. So that's only one way, but there are four more ways to do it. Now, in the second example, we only have one element and the target is 1, so we can only put the plus sign in front of the first element, and that's basically the other option is to put minus 1, but then minus 1 will not be equal to the target. The procedures are the following. The nums are from the length of the array is from 1 to 20, and the elements inside of the input array are from 0 to 1000, and also the sum of all the elements inside of the input array is from 0 to 1000. We probably had something for the target as well. Let's just check that quickly. So the target is from minus 1000 to 1000. Now, to solve this problem, we will first see what is basically asked from us. So we have to put the expressions. We have to find a number of ways that evaluate to the target. So basically, for each of the numbers inside of the input array, we have to put them in a certain configuration. Either give them the plus or the minus sign, so we can get the target. So basically, if we solve for a subproblem, let's just say we are combining the first 3 elements in a certain configuration, adding plus or minus, then we would have the remainder of the elements in the input array as the second subproblem to form an expression that evaluates to target minus the sum of the first expression. So basically, we can split into multiple subproblems evaluating to a different evaluation of the expression that's when summed up equal the target. So our problem is to find those configuration. And if it didn't hint you towards the dynamic programming question, basically this is kind of the same setup as we had for the knapsack problems. But in this case, we have only one additional requirement is that we have to choose every single element that we have, every single item that we have in the input array. So we'll go through the different solutions, different ways of solving this problem. But before we do that, we will first categorize this problem. So we know for the category, basically it's a knapsack problem. And the states that we have to track, the states are basically the current sum. We have to know what the current sum of the subproblem that is, so we can solve the initial big problem. And we also have to know where in the array we are. If you're traversing through the array, we are recursion, so we know we have to follow the index. Now, the decisions are either to take the positive version of the element or the negative version of the element. So we have two choices. And the base case is that we have reached the final index and the current sum is equal to the target. That basically means that there's at least one way that how can we reach the target by using this current configuration. And if we have arrived at the final element, but the current sum is not equal to the target, it's larger or smaller, then we just return 0, because we know that the current configuration doesn't yield the target. So basically, these three steps leads us to the recursion solution of this problem. So we'll have the helper function, and we will just forward the current index and the current sum, and also the target. And we are kind of doing the basic recursion that we had also in the backtracking problems. So we have these two base cases. As we said, we are checking if the nums, if the current index is the last index, and also if the current sum is equal to the target, which basically means that we have that the current configuration, that the current setup of minuses and pluses that we have added for all of the items inside of the input array yield the when summed up yield the target sum. So we just return 1. Otherwise, we are at the last index. We don't have the current sum equal to target, so we just return 0. Now to the recursive part of the function. If you want to solve for the first sub problem, we can either choose this element as plus or minus, and then combine it with whatever we have in the rest of the input array. That's why we have the recursion. So basically, to solve the whole problem, we are combining the first part of the first part of the problem, which is only one element, and we are either giving it plus or minus, and we are checking then for the rest of the array. We are recursively solving the rest of the array. So to basically define that in the recursion, we'll just increase our index because we're already done with the first element, and we are in the first option we will add the current element, and in the second we will basically add it a minus. So we will subtract it from the current sum, and the target also remains the same. Now the total numbers, how we can reach the target, is basically these two summed up. So basically the total numbers of the ways we can reach the target by using the positive value of the current item, or the negative plus the number of ways that we can reach the target sum by using the negative value of the current item. So we'll just add those two. Now, because we have these two options, we will basically kind of get to the n time complexity, which for larger input arrays will not perform well, of course. So the first thing that we can do is to use the memorization. So for a lot of sub-problems, we will recalculate them many times. And to solve that problem, we will basically use a memo. As you can see here, we are using the tuple, and tuple is the custom class that I implemented, but I didn't paste it here, so we can have more space and only focus on the important stuff. But basically, the tuple here is represented by the index and the sum. So we are kind of asking ourselves, if we have a certain index, starting from that index, how many ways are there to get the target? And basically that will be the key. The tuple will be key, and the value will be the number of ways that we can get the target sum by starting from that index and up to the and getting the sum that's passed as the second parameter to the tuple. So we will have the same helper function call here, and we'll have same base cases. But now, before getting to addition and subtraction, we will check if we contain the index, if we contain the corresponding key. And to check if the corresponding key is present in the memo, we will basically pass the current index that we are at before adding the values of that index, either in a positive or negative form. And then we will check how many ways are there to get the specific sum starting from that from the current index. And the specific sum that we are looking is the target minus current sum. So we already accumulated the current sum. So now the difference that we have to add up to get the target is basically just given by target minus current sum. So if we have, for example, target 5 and the current sum is 2, so we have only encountered one element and the value is 2, and we added it as plus 2. So the number of ways that we are interested is for the sum 5 minus 2. So we are looking how many ways we can get the sum 3 starting from the, for example, second index. And if that key is present, we will just return it. Otherwise, we will have to go through the calculations, just as we had in the recursion approach, and we'll just add the addition and subtraction to the total, and we'll return the total. But before we will do that, we will cache the computation so we don't have to do it again. And to cache the computation, we'll just use the current index and the total number of ways that we have just calculated. And now the sum is actually the exact same sum that we try to retrieve. So the sum will be basically target minus current sum. So the sum that we have calculated before reaching this recurrent call, and when added up to the sum, it will equal to the target. So that basically means that we will know in how many ways we can get the rest of the sum that when added to the current sum adds up to the target. So the next time when we check for this index, we will and we are trying to find that sum, we will be able to retrieve it. Now, this is all good, and we are kind of reducing the time complexity here. We are not recalculating every single branch of the tree that we did in the recursion, but basically this is a top-down approach, and as always we are trying to do the bottom-up approach. But to do the bottom-up approach, we will have to transform the initial problem into something else. So the initial problem is basically stated as this. We are having some positive numbers, and here I'm declaring the sum of the positive numbers, and then we have selected the rest of the array elements as negative. So the sum negative will be basically the absolute value, the sum of the absolute values of all the elements that we have chosen as negative. And then we can just extract this minus, because all of these, the sum of negative numbers will be negative. And then we have to basically get the target. Now, if we add for both sides of the equation, if we add some positive plus some negative, which is basically the total sum of all the elements, then we will get target plus some positive, some negative, which we can just exchange to sum of the all elements inside of the nums. And on the left side, we will basically cancel out this negative and this negative here, and we'll get 2 times some positive. So the remainder, then when we divide by 2 both sides, we will get some positive, and then target plus all the elements inside of the input array divided by 2. So basically the problem is now transformed to find the number of ways that we can get this sum positive. So, and the sum positive is basically this, it's equal to this. So if we find the number of ways that we can get the sum positive, all the elements that are chosen as positive will not be able to be. We will not be able to choose as negative, which basically leave us with all the other elements that will be negative, which is the initial problem. So we kind of cut down this equation to the equation of finding the number of ways that we can get target plus some nums divided by 2. That's the sum. That's the positive sum that we are looking, and basically the rest of the array will be negative numbers. So when those two are added up, some positive plus actually minus some negative, we will get the target. So to find the number of ways that we can get the sum positive, we will basically declare the sum to be equal to 0. This is only the helper variable to get the sum of all the elements inside of the array, which we are doing in this for loop. And then we are checking if the target is larger than the sum. In that case, we cannot combine, and there's no configuration that will get us to the target, because target is larger than the sum. Other cases when we have some target divided by when we have basically an odd part. When basically calculating this, we'll have an odd number, which cannot be, because when divided by 2, we will get 0.5 something, which is impossible because all of the elements inside of the input array are integers. So in that case, we will know that we will not be able to get the sum positive. So we'll just return 0 as the number of ways that we can get sum positive. Otherwise, we will just calculate the sum positive as we did in the formula above. and then we will create our DP, the interpolation and the bottom-up approach. As you can see here, we are having the +1 to offset the -1 that we are doing here in the DP calculation. So basically, we will have item by item. Those will be our rows, and the amounts basically will be from 0 up to the sum positive. So this is the target that we are, and these are the items. So now to get the DP, we'll traverse first through the items that we have that we can choose from. But before we do that, we will have also this initial step for the first column. The first column is basically amount 0, and to get the amount 0, there's only one way. Basically, we're always not choosing any of the elements. So this is kind of like a offset, so we can easily calculate the rest of the columns. So we are starting now from the amount 1 up to the. We're actually starting from the first row, so we are skipping the previous one. And we are starting from the 0 amount, and we are going up to the sum positive. Now, to calculate the DP ij of each of the cells inside of our matrix, we'll basically first get whatever we have in the previous row, which for the first row that we have offset will be 0. And then we will see if the current j, basically the sum, is larger than the whatever we have as the item. If it is, then we can basically see if we can combine the current item with the difference to get the j sum. And to do that, we'll just reference the last row and the column that corresponds to the element that, when added up to the current item, sums up to j. And it's we easily get it by just decrementing the current item from the j. And we will add that to the current value of dpij. Then finally, after we are traversed through all of the both of the two for loops, we'll just return whatever we have as the last value. So basically that corresponds to having iterated over all of the items and also all of the columns. So we are at the last column, last amount, the one that we are looking, the sum positive, and we have also iterated over all of the items. So we know that's the number of ways that we can get the sum positive. Now, basically this will yield m times n for both the time and space complexity, and we can reduce the space complexity to basically sum positive. If n is basically sum positive, so that's the number of columns, because we only need one row. For each of the calculations, we will only need the previous row. So again, we are iterating over the elements that we have as the items that we can have. Inside the input array. And as you can see here, the only difference now is that because we only have one row, we don't want to overwrite the previous computations. So if we are basically, because before we have used the last row to do the computation, but now we are kind of rolling back. We're using that trick of like rolling back, starting from the last column and up to the first column, because basically the columns that are before, for example, if we are starting at the last column, the columns that are before in the only row that we are using as the DP will represent basically the previous computation, the previous item computation. So for the current item, we can freely choose it, because if we combine it with the value from the previous row, which is corresponding to some column here, we are good, because this is the first time that we are choosing this item. We can be sure because we are starting from the backwards. We are starting from the end and going up to the first element. If we started like this, from like the usual way, start to the end, then we would basically overwrite this column that comes before this one, and that means that we kind of have used already the item, so we cannot reference it back from this cell, from this column again, because that means that we'll be using it 2 times, which we cannot do. So, and then we'll just return again that sum positive, basically the last column after we have traversed through all the loops, which basically is m times n time complexity, where n is basically the number of items that we have in the input array, n is the sum positive. And the number of elements inside the DP will be n, so that's the number of columns.